Hey everyone, so today we have Charlie Yun with us. He's an assistant professor at KAIST and was previously a postdoc and PhD student at MIT, has done a lot of work in optimization and machine learning, and is going to be talking to us today about some interesting comparisons between Minibatch and local SGD, which is very relevant for the problem of federated learning. So excited to hear more, and yeah, we'll kick it off to you, Charlie.
All right, thanks Virginia for the nice introduction. So hi everyone, my name is Charlie. So I'm an assistant professor that recently joined KAIST Kim Jae-chul Graduate School of AI. So thanks for inviting me. It's a great honor to present my paper at the Flow seminar and share our results with everyone. So today I'm going to talk about our paper titled Minibatch versus Local SGD with Shuffling, Tight Convergence Bounds and Beyond. So this is a paper that we presented at iClear 2022. And this is about the theoretical analysis of federated learning algorithms under the shuffling-based sampling schemes. So this is joint work with Shashank, who's a PhD student at University of Wisconsin-Madison, and Suvid, who used to be my PhD advisor at MIT. So please feel free to interrupt me, either through the chat or raising your hand if you have any questions during the talk. So I'll first start by describing the federated learning setup that we're going to consider today, although I'm pretty sure that almost all of you are pretty familiar with the setup. So there's a central server and M different local devices or machine. So you can think of this server as maybe a server run by Google or Apple, and the local devices as your smartphones. And each device or machine has its own local objective function, FM, and which is the mean of n local component functions. And there's a global objective function, which is the mean of m local objective functions. So in the supervised learning example, where we want to train a neural network with supervised training data sets, x, the optimization variable x would correspond to the parameters of the neural network, and each component function, fmi, would correspond to the loss function defined on a data point, okay? And a unique characteristic of this federated learning setup is that the local components can only be accessed by the corresponding local machine it belongs to, not by other machines nor the server. So for example, people can have like a bunch of photos in their phones and they don't want to share their photos to someone else or even the server. The data is basically private. And so in this privacy preserving setting, the central server nevertheless wants to minimize the global objective function f, the mean of the local objective functions fm. So for example, even if Google doesn't have access to the private photos, they could still want to make their global classifier or their global prediction models work better by somehow utilizing the information from the user's photos. So this is the standard federated learning setup that has become very popular during the last several years. So how does the server do that? So I'm pretty sure most of you would be familiar with the way how to get around this issue because it's Flow seminar. So yeah, the server uses an algorithm that asks you to update the parameters locally on your machine while using your private data, and then asks you to share the updated parameters only. And so this is the key idea of local SGD or federated averaging algorithm, which I'll describe in more detail now. So in this federated learning setup, the algorithm called local SGD, or also known as federated averaging, has become one of the most popular algorithms. The key features of local SGD are the intermittent communication and local updates. It'll be clear what I mean by now, by the end of this description. So the local SGD consists of multiple communication rounds. So at the beginning of the communication round, the server broadcasts its global iterate xk to the local machines. So all the local machines actually receive the global iterate xk. And upon receiving that global iterate, the local machines make local updates using the stochastic gradient computed from their local component functions. So in more detail, upon receiving this xk from the server, machine M sets its local iterate to be xk, and then makes makes B local updates. So at each iteration, the machine chooses some index I of t from the pool from 1 to n, and then updates its local iterate by computing the gradient of the local component function that has index I of t. And this index I of t is used as a stochastic gradient, and which serves as the estimate for the local objective function fm. Okay. So after making these B updates, the server aggregates the updated parameters and takes the average of those aggregated updated parameters, and then the server sets the next global iterate sk plus 1 to be that average. Okay, so this is how the global iterate is updated at the end of the communication round. So for the next communication round, the server starts by synchronizing the machines with the average, the updated global iterate sk plus 1, and this process is repeated multiple times. So this is how local SGD works. Yeah, in federated learning setup. Okay. So so far I've described the local SGD algorithm, and in this paper we want to compare this local SGD algorithm with a simple baseline, which is called the Minibatch SGD. So this pseudocode is what happens for a local machine when they make local updates, right? And suppose we change this update equation to be this. So for local SGD, since each of the local machines make SGD updates, the gradient is evaluated at the last local iterate that the local machine has. But in Minibatch SGD, the gradients are actually evaluated at the last global iterate, right? So this update seems to be doing some, like making some progress or updates, but this is actually accumulating the gradients of B different component functions evaluated at the last global iterate xk. So if you consider the aggregation after the B update, then this, from the central server's point of view, this is actually equal to collecting B gradients from each machine. So there's MB gradients in total, and the central server actually uses those mini batch of MB gradients to make a single update to the global iterate. So the actual update is done only once per communication round. So we call it Minibatch SGD because it's just SGD with minibatch size MB. So this sure looks like a dumb algorithm, right? But it turns out that at least theoretically, it performs comparable to this local SGD algorithm, or sometimes even better. So I'll get into these comparisons in more detail later. So, and also you can note that these two algorithms actually use the same number of gradient computations per communication round. So this Minibatch SGD algorithm naturally becomes a baseline for local SGD. So, and it would be interesting to compare the performance of these two algorithms, both theoretically and empirically. And when I was talking about choosing the index I of t from the pool from the pool of the indices from 1 to n, I kind of swept the details under the rug, right? So I'll next discuss what kind of different approaches that we can use. In other words, what kind of sampling schemes that we can use to choose these indices. Okay. So in the context of finite sum optimization, which is exactly our setting, there are actually two main variants to the sampling algorithm. So the first one is with replacement sampling, where each of the indices I of t is chosen uniformly at random at each iteration. So this is how the sampled indices look like, and the sampled index here is completely independent from the past iteration and the future iteration. So this makes the stochastic gradient evaluated with the with the chosen component function be a unbiased estimator of the true full gradient. And this makes the analysis much easier. In contrast, practitioners actually use without replacement sampling, which is also called this random reshuffling. In without replacement sampling, we choose a permutation of the n indices uniformly, and we use this chosen order to access the gradients, access the component functions, and compute the gradients of them in a sequential manner. So let me show you an illustration. So we have 5 indices. So n is equal to 5 here. So we can see that the first 5 indices that are chosen is a shuffled version of 1, 2, 3, 4, 5. And the next one is also a shuffled version. And the next one is another shuffle. So this one pass through the entire 5 indices is called an epoch. So this example shows 3 epochs of the algorithm. Okay, so one key observation about this without replacement sampling approach is that the indices actually become dependent to each other. So if suppose you have chosen this F3 in the first iteration, then since we're using without replacement sampling, this means that for the later iterations of the same epoch, we'll never get to choose F3, right? So in other words, this means that the indices chosen at the iterations in the same epoch become dependent to each other. So that's why any theory that is developed under the assumption of independent gradient oracles don't apply to without replacement sampling algorithms. Okay, so this makes the analysis of without replacement sampling much more difficult, even though this sampling scheme is much more popular in practice. So in summary, with replacement versions are the ones that are mostly studied in theory. In contrast, without replacement or random reshuffling versions are the ones that are used in practice. Okay. So given these backgrounds, let me summarize the existing results. Okay. So the local updates that are done in local SGD or federated averaging actually introduce challenges in this convergence analysis. So there have been numerous papers analyzing the convergence rate, but however, almost all of them are based on the assumption that the stochastic gradients are unbiased and independent. And this corresponds to the with replacement sampling. And out of the many results based on this unbiased and independent oracles, the line of work that we got the most motivated from was the ones by Blake Woodward and co-authors. And so they compare the convergence rates, of course, under the with replacement setting. They compare this convergence rates of local SGD versus Minibatch SGD, and showed that it is hard for local SGD to converge strictly faster than Minibatch SGD, which is quite surprising because Minibatch SGD looked like a dumb algorithm. Okay. And also there's an expanding line of research on the analysis of without replacement SGD and its variance. So the punchline of these papers is that the random reshuffling algorithms converge faster than the with replacement versions if the number of epochs is sufficiently large. However, most of these results are on the single machine case, the single machine SGD case, and there are only a couple of concurrent papers that consider the extension to the federated learning setups. So we just saw that there are 2 lines of research. So the one studies this distributed or federated SGD under the assumption of independent gradient estimates or with replacement sampling. And the other line of research studies without replacement SGD, but mostly on single machine case. So our paper is exactly where the two different lines intersect. So we study the minibatch and local SGD under this random reshuffling sampling scheme and provide the tight analysis of convergence rates. So we provide upper bounds and almost matching lower bounds. And also at the end of this paper, we propose a modification to the shuffling scheme that allows us to bypass the lower bounds in certain homogeneous cases. Okay, let me now briefly recap this problem setup and state some assumptions. Okay, so we have this global objective function f to minimize, which is the mean of m local objective functions. And each local objective function is also a mean of n local component functions. Okay, we have this photo. Let's have this, keep this picture in mind. So so we assume so let's talk about this function classes that we consider in this paper. So we assume that the global objective function f satisfies the Polyak-Lorentz condition. So we'll call this the PL condition. And this PL condition can be thought as the class of non-convex functions, but they're not as scary as the general non-convex functions. Okay, so the PL functions are actually much easier to optimize, and sometimes at almost as easy as the strongly convex functions. So you can think of this function class as the non-convex but not difficult functions. Okay, and we also assume that each of the local components fmi is L-smooth. Okay? So it's a very popular assumption in optimization. So, and we also define the condition number to be kappa, which is the ratio of L to mu. We next make some assumptions on the intra-machine and inter-machine deviation. So intra-machine deviation tries to capture the deviation of the local components within each machine. So for intra-machine deviation, we assume that the gradient of the local component functions are very close to the gradient of the corresponding local objective function. So the norm of their difference is bounded by nu. So in real life, you can think of this assumption as the case where one person has a lot of cat images and the other has a lot of dog images, etc. Okay. And for inter-machine deviation, which is also called the heterogeneity, is we assume that the mean of the norm of local objective gradients are upper bounded by this tau plus rho times the norm of global objective gradient. So this looks kind of scary, but this is also actually similar to the bounded gradient dissimilarity assumptions that have appeared in the literature. And also to help understand what this is saying, if you consider this homogeneous case where fm, the local objective functions, are exactly equal to the global objective function, you can quickly check that this inequality holds with tau equal to 0 and rho equal to 1. Okay. All right. So so far, let me recap the different symbols. So we have m machines, and there are n local components per machine, and we run the algorithms for k epochs, and we use b gradients per machine per communication round. So let me recap the local and minibatch SGD in the random reshuffling version. Okay? So in the beginning of the kth epoch, each machine samples a uniform samples a random permutation of n items. So we denote this permutation sigma mk. So this is the order of the permuted indices. So after that, the central server broadcasts the first global iterate sk, 0, and upon receiving this global iterate, the local machines make b local updates. So it initializes its local iterate to be the global iterate that it just received, and then it makes b updates. And the order that is the order of the indices that is indices of the component functions is determined by the sigma mk that is selected or sampled in the beginning of this epoch. So for local random reshuffling, the local machines use the last local iterate to evaluate the gradient. And for minibatch random reshuffling, the machine instead uses the last global iterate to evaluate the gradient. So after making these B updates, the server aggregates the parameters and averages the parameters to update the global iterate to be xk, 1. Okay. So this is a single communication round. And since there are n components and b gradients per communication round, there are n over b communication round per epoch. So for an epoch, we repeat this communication round n over b times, and then epoch ends at xk, n over b. And then we start the next epoch with the last iterate of the previous epoch. And so we repeat this k epochs until all of them finish, and then we return the very last iteration, the very last global iterate of the algorithm. Okay, so this is local random reshuffling and minibatch random reshuffling. All right, so we finally finished setting up the table. So it's time for the main results of this paper. Okay, I'm going to show you the upper bounds on the convergence of this minibatch random reshuffling and local random reshuffling algorithm, provided that the number of epochs k is larger than a threshold, which is in the order of kappa. So for this large epoch regime, we prove this upper bound on the convergence rate. Okay? And we show this lower bounds for both algorithms that match the upper bounds in the large epoch regime up to a factor of kappa squared. Remember, the kappa is the condition number. And next, we propose this algorithmic modification called synchronized shuffling that allows the algorithms to converge faster than the lower bounds in the homogeneous settings. Okay, let me state the first upper bound. Okay, so these are the assumptions that I covered already, right? So we assume that the global iterate, the global objective function f is Polyak-Lorentsev, and then each of the individual component functions are L smooth. Okay? And we assume this intra-motion deviation and heterogeneity. Okay? So if you consider running this random reshuffling algorithm with the number of epochs k satisfying this inequality, so k has to be large enough, and it has to be in the order of, at least in the order of kappa. And we choose this constant step size this way, then with high probability, we have this convergence bound. So the suboptimality gap is upper bounded by this bound. Okay? And whenever we talk about the convergence rates, I'm only going to consider the second term in the yellow box. This is because actually the first term can be made arbitrarily small by changing the step size. So the mn k squared term here in the log factor is actually the same as the denominator of the first term in the upper bound. So that's why changing what's inside the log, you can make the first term arbitrarily small. So whenever I discuss and compare these bounds, I'm only going to consider the second term. Okay. So this is basically the result that I just showed you. So a couple of remarks on this results. So if you compare this minibatch random reshuffling and single motion random reshuffling, if you compare these rates, you can definitely see that there's an additional factor of m. So the minibatch random reshuffling is faster by a factor of m. So this shows the advantage of parallel computation. Okay. And if you compare this rate with against this with replacement version of Minibatch SGD, The Minibatch SGD is known to have this tight convergence rate. Okay, so this is you can notice this MNK squared versus MNK. So as a result, the minibatch random reshuffling is faster if K is sufficiently large. If K is larger than kappa squared, then we can show that we can see that this minibatch random reshuffling is strictly faster. And one interesting thing to note here is that the bound doesn't have any term depending on the heterogeneity parameters, tau and rho. Okay, so this means that the minibatch random reshuffling algorithm has some interesting property that it's completely immune to heterogeneity. So this is a very nice property, right? And this actually is consistent with the observation by Blake Woodworth and co-authors that the width replacement version of Minibatch SGD is also immune to this heterogeneity. And one might wonder that this bound doesn't have any dependence on the communication intervals or the minibatch size B, right? So this is because we wrote this the convergence rate in terms of the number of epochs. Okay, so we can alternatively write this convergence rate in terms of the number of communication round R. Okay, so if we plug in, if we make the appropriate conversion to make this rate into a rate in R, then we can see that there's a B squared term. So the number of communication actually decreases with increasing batch size B. Okay. And I'm gonna briefly talk about the main proof ideas. Okay, so this is the update equation for minibatch random reshuffling. So remember that xk, 0 is the starting global iterate at the beginning of the kth epoch, and sk, 1 is the next global iterate. Okay? This is the update equation. And this is, of course, the next update equation. So, however, we can actually decompose, well, in other words, we can actually add and subtract the gradient evaluated at xk, 0 instead of xk, 1. So this allows us to kind of decompose this gradient into quote unquote signal and quote unquote noise. Okay. And by substituting the definition of xk, 1 into here, we can write this one as this. So it's the sum of the signals and minus the sum of errors or noise. Okay. And we can actually repeat this process until the end of an epoch. And this allows us to write the update over the entire epoch as this sum and some noise. Okay. And actually, we can notice a simple identity that for any given permutation, if you sum all the elements over an epoch, and this gives the full sum, right? For any sigma mk that is chosen, the sum over I from 1 to n is exactly equal to just sum over all the I, for sum over all the indices, like without any permutation. And by the definition of the local objective function fm, this is actually equal to n times the full gradient of fm. Okay. And by using this permutation identity, we can write, and another thing to know here is that the error term is kind of small due to the smoothness. So by using these two key observations, we can write this per epoch update as one big gradient descent step plus some small noise. Okay, so that's the key idea. So basically, using this permutation identity, we can write the update during an entire epoch as just one big gradient descent step plus some controllable noise. And so it's left to control this noise, right? So what we do to do that is to bound this norm of RK. And bounding this norm of RK boils down to bounding the norm of some partial sums of this form. Okay, so if you look at this sum, you can first see that for a fixed machine M, each of the local component gradient is a vector, right? And so for a fixed M, we have n different vectors. And in this inner summation, we can see that we shuffle these n components and add only b of them. So this is a partial without replacement sum of the vectors. And if you now look at this outer sum, we're taking the mean of m different partial without replacement sums, and these partial sums are independent of each other because these shufflings are sampled independently. Okay, and it's easy to check that the mean of this average is actually equal to the gradient of the global objective function f. So we can add and subtract the gradient of f here and apply this triangle inequality. So the grad f is the actual mean, or it's the expected value of these the average of partial sums. Okay, so it remains to bound. The norm of this distance to the true mean. And using a concentration inequality lemma that we proved in the paper, we show that with high probability, the norm is bounded above by a factor that shrinks with m, the number of machines. So that's why we have the m factor in the convergence bound. And this lemma that we proved in our paper may be of interest because we extended the existing vector valued half-thing circling inequality to the setting where there are multiple independent without replacement sums. Okay, so this is, let me now move on to the upper bound for local random reshuffling. So yeah, so we have this similar setting, and for epochs large enough, we have a similar upper bound, but this time we have these two additional terms. Okay? And these two additional terms come from the noise in the local updates. So if you compare the local random reshuffling upper bound with some other various algorithms. So first of all, if you compare against the last iterate bound on the width replacement version of local SGD, we can see that somehow surprisingly, the last two terms exactly match each other. And for the first term, you can see that local random reshuffling is faster if k is greater than kappa. And we can actually note this, there's a trade-off in B in case of local random reshuffling. So the C sub C here is the cost of a single communication round, and C sub E here is the cost of gradient computation over on epoch. So this terms inside this complexity is obtained by converting this bound into the one in R, the number of communication round, and then applying the standard conversion. And so this is the communication complexity, and this part is the epoch complexity. So you can see that for if B is too large, then the epoch complexity becomes too large, and if B is too small, then the communication complexity becomes large. So for local random reshuffling, so we can see that one has to balance between these two costs by choosing the communication interval B in a careful manner. And also, one observation from this upper bound is that if you choose B to be too large, then it doesn't help speed up the convergence. So for example, if B is equal to N, then if you plug this one, if if you plug this b equal n, then even the case where there's no tau, even in the case where tau is 0, which corresponds to the homogeneous case, the rate of convergence becomes 1 over nk squared. And this 1 over nk squared is actually the same as the single machine random reshuffling algorithm. So in other words, if there's no speed up by the number of machines m. So you're just better off running random reshuffling on a single machine instead of running local random reshuffling on m machines. So in other words, we gain nothing out of this parallel computation. And it is left to actually compare these two rates, actually, right? So we can see that if b and tau are both sufficiently small, the local random reshuffling's rate can be the same as minibatch random reshuffling. However, it seems that under our settings, under our assumptions on the function space, it seems difficult for local random reshuffling to outperform minibatch random reshuffling. Okay, yeah, the proof idea is actually pretty similar, but this noise term RK now has two different types of noise. So one from the minibatch update, and the other that comes from the local updates that are done inside each local machine. Okay, so this results in the same term as the minibatch random reshuffling, and this results in the two additional terms. Okay, let me now move on to the lower bound. So we consider the same set of functions and assume constant step size, and also that the algorithm always returns the last iterate. So under this setting, we can see that if k is less than a threshold kappa, then the lower bound is in the rate of m and k. However, if you go above that threshold, then the lower bound becomes k squared. So there's a phase transition between the small epoch regime and the small epoch regime and large epoch regime at kappa. So yeah, so if you compare the upper and lower bounds for k greater than kappa, in other words, for the large epoch case, the two rates are actually almost tight. They only differ by a factor of kappa squared, and they match. So all the remaining factors exactly match each other, right? And there's one interesting observation for the small epoch regime. So it is known that for the width replacement setting, the optimal rates for Minibatch SGD is mu squared over mu m and k. So we can actually notice that this optimal upper and lower bound is equal to the lower bound of without replacement sampling in the small epoch regime. So this implies that at least in the small epoch regime, there's no hope for without replacement minibatch random reshuffling to converge strictly faster than the with replacement counterpart. And one interesting open problem is to prove a matching upper bound. So in the small epoch regime, so the proving on the upper bound that matches this rate for k smaller than kappa still remains an open problem. Yeah, I tried proving it myself, but it seems that the small epoch case requires some new proof techniques. Okay, so this is the lower bound for local random reshuffling. So let me focus on the large epoch regime. Okay, for the large epoch regime, we can again see that these terms actually match each other up to a factor of kappa squared. And also, we observe from the upper bound that setting b to be equal to n is not a good idea. And the lower bound actually gives confirmation to this observation. So for tau equal to 0, so there's this tau term, which corresponds to the homogeneous case. Then if we set b equal to n, then the lower bound becomes 1 over nk squared. So this lower bound doesn't have any m term. So the local random reshuffling indeed loses the merit of parallel computation. Okay, so now that we have seen the upper and lower bounds for the vanilla algorithms, let me now talk about some algorithmic modification that can further speed up in some homogeneous cases. Okay, so we call this technique synchronized shuffling. So this technique can speed up algorithms when the component functions across different machines are similar to each other. So for simplicity, let's consider the case where we have component-wise homogeneity. So all the FMIs are indeed equal to FI. So this corresponds to the case where all the machines have the same data set, exactly the same data set. So in the proof sketch of the upper bound, I use this identity called the permutation identity. So namely, that summing the component gradients over an epoch actually gives the full sum and then the full gradient. So because this identity was quite useful for proving faster rates of random reshuffling algorithms, the motivation for synchronized shuffling is to exploit this permutation identity more often. Okay, let me illustrate how we can do this. Okay, we can so for the case of independent shuffling, the vanilla algorithms, we choose the shufflings, we choose the permutations sigma mk just independently. Okay, so these are the independent shuffles. So if you consider taking partial sums over the increasing range of i's, we want to do that because these partial sums actually appear in the proof of the upper bound. More specifically, these partial sums appear in when we bound the noise term RK. And we want to apply the permutation identity to these partial sums as much as possible. However, you can actually notice that because these individual shufflings are all independent of each other, we cannot apply the permutation identity in the middle of an epoch. So we have to wait until the end of the epoch to be able to apply this permutation identity. So to allow ourselves to apply this identity multiple times during a single epoch, we devised this synchronized shuffling trick. So the idea is to sample a base permutation sigma at the central server, and then to broadcast it to the machines. At local machines, each machine sets its permutation sigma mk to be some shifted versions of the base permutation sigma. So let's see an illustration. So you can see that the permutation for machine M and machine 1, machine 2, and machine 3 are actually shifted versions of each other. So so sigma 2k is a shift of sigma 1k by 2, and sigma 3k is also a shift of sigma 2k by 2. Okay, so this trick actually allows us to get the full sum in the middle of an epoch. So suppose we compute this partial sum over this yellow rectangle. So you can see that all the 6 component functions are in the sum. So that this allows us to get to apply this permutation identity and get the full gradient. And we can get this full gradient every n over m iterations. So the fact that we get this full gradient multiple times during an epoch allows us to further speed up the algorithm. And I also have to note that there's a concurrent paper by Peter and his co-authors that makes use of the same idea for a different purpose. So they use this idea to build some compressors for communication efficient optimization. Okay, let me show you how this synchronized shuffling can further speed up the algorithm. So if you apply synchronized shuffling for these 2 algorithms, you can see a speed up by speed up here. So the factor of m in the denominators are now factor of m squared. Okay, so these improved rates actually bypass or break the lower bounds, because the lower bounds only has the factor 1/m. So in terms of m, yeah, these revised upper bounds are actually faster than the lower bounds. And we can also compare these two rates and see that local random reshuffling can still match the performance of mini-batch random reshuffling if B is sufficiently small. And although I assume this full component-wise homogeneity for simplicity, our actual theorems in the paper are proved under some assumptions that actually allow some slight heterogeneity. So a similar speed up may be observed for the case where the machines have some slightly perturbed versions of the same data set. Okay, that was it for the theoretical results. And well, if I still have time, I want to introduce to you some experimental results with some toy examples. Okay.
Yes, yes, please go ahead. We have still
okay.
some roughly like 10 minutes. So please
go
ahead.
Yeah. Right. Thanks. Okay. So we ran some toy experiments using the worst case example that we used to prove our lower bounds. And we first compared the 4 random reshuffling algorithms. So mini-batch random reshuffling, local random reshuffling, and those 2 algorithms with this synchronized shuffling technique. So we can, so let's see the rates of these algorithms first. And what we can notice first is that the performance of local mini-batch random reshuffling and local random reshuffling are similar when B is small. However, the performance of local random reshuffling actually degrades when B becomes large. So this is because for the smaller B, this term in the bound of local random reshuffling was the dominant term. But as B becomes larger, the second term becomes dominant. So this degrades the performance. And the second one, if we compare the rates, compare the performance of mini-batch random reshuffling without and with synchronized shuffling, these are red and green curves. We can see that there's a consistent gap. There's this consistent gap irrespective of the value of B. So this is kind of consistent with our theoretical results. And if we compare the local random reshuffling without and with synchronized shuffling, what are X and Y axis? Okay, X is K. Oh, I'm sorry, I've never mentioned this. X is the K, the number of epochs, and Y is the function value. So the suboptimalated gap in terms of the function value. Okay. So yeah, hopefully this answers your question. Yeah, so we compare this local random reshuffling without and with synchronized shuffling, and these are blue and black curves. Okay, so for B small, the local random reshuffling with synchronized shuffling indeed is faster, but if B becomes large, the 2 algorithms become similar. So this is because for small b, the first terms are the dominant terms, but if b gets large, these second terms, which are equal to each other, become the dominant term. Okay, so you can see that the experimental results actually align quite well with our theoretical results. Okay, the next set of experiments actually compare the minibatch, local, and single machine random reshuffling. So we can quickly see that as B becomes larger and larger, the performance of local random reshuffling gets closer and closer to the single machine random reshuffling. And the last set of results is a comparison of the without replacement versions and with replacement versions. So our prediction was that for small epochs, so for case small, without replacement versions should perform similarly to with replacement versions. but for large epoch regimes, it should show better performance. So the figures actually show the similar trend, right? First, for K small, the two versions of the algorithms perform quite similarly, but as K gets larger, the without replacement versions show better performance. Okay, this is consistent for other values of B. Okay, that's it for yeah, that's all I have for today. So I'm happy to answer any questions that you might have. Yeah, thank you for your attention.
Thank you, Jared. That was a really great talk. And yeah, so please, if you have a question, just post it to the chat or just raise your hand, and then I'll try to unmute you. Yeah, maybe I would start with few. So yeah, with like all the local methods, it seems like you can kind of break global bound or improve the rate by a variance reduction. Did you actually consider this as an extension, also with like a
okay.
local reshuffling?
Oh yeah, so that's a very good question. For variance reduction methods, a very interesting thing is that it's really hard for random reshuffling versions of variance reduction methods to outperform the with replacement versions. So as far as I know, the best sample complexity or gradient computation complexity for without replacement versions of variance reduction methods is actually worse than with replacement versions. So this is quite interesting, and I hope to investigate this problem in the future, but I haven't had any chance to do that. Yeah.
So what I also meant is not just like really like just trying to do like variance reduction locally, but also this kind of trick, for instance, something similar to what scaffold does. That
Scaffold.
you try like you try to like globalize your objective. So somehow that the local updates resemble more the kind of what you would do if you would do like a global update based on all of the data. So
okay, so yeah, so that way, yeah, put that way, I think the synchronized shuffling also can be seen as a technique to reduce the variance. Yeah, that's an interesting observation. And I'm not really sure how we can precisely compare our synchronized shuffling method versus this scaffold, but yeah, that's an interesting comparison. Yeah. Thanks for the suggestion. Yeah, that's a great connection.
And yeah, so maybe let me see what there is. It doesn't seem there is a question, so I'll maybe yeah, I can ask one more. So do you so in many scenarios you have different number of data points locally. So is what you presented like trivially extensible to that scenario or no?
Oh yeah, that's a very difficult question, because so the key point of the shuffling based methods is that you run the algorithm at the unit of epochs, right? So if you have different number of data points per the machines, then this could be a kind of a design question or something, right? So if one machine has like twice the number of data compared to other machine, would you let the machine to run the same number of epochs or the same number of iterations? So I would say it's for the purpose of analysis, the same number of epochs would be much easier to analyze, but a more practically like reasonable choice would be to restrict the machines have the same number of iterations. So I guess in that case, the analysis would be quite complicated, I guess. Yeah.
Although I think it's the thing is like what people do in practice is really like you do allow each worker to run the predefined number of epochs, right? But the thing is but then you run like you run into the issues that actually if you use the same step size and you take many of local steps, and then suddenly it's the objective you actually end up optimizing is not the one that you were originally intended to.
Yeah, that's a good point. Actually, so one thing I had to admit or point out is that our comparison of local versus Minibatch SGD was only done under the setting where the communication interval is strictly less than the number of data points. So the number of epochs run per communication round is strictly less than 1. So we intentionally did so because for minibatch random reshuffling, if you allow the communication interval to be an entire epoch, then this algorithm basically becomes gradient descent. So yeah, so this gradient descent has a linear convergence rate, and so the local random reshuffling is no match. So that's why we intentionally focused on the case where B is less than N.
Thank you. Let me see whether there is. It seems we have no other question. I'm thinking what I'll ask them one more, just a technicality. So I saw that in your assumption you're using like for instance heterogeneity, that you're using just a norm but not norm squared. Is there actually a particular reason for that?
Oh yeah, so that's a very good question. Let me first pull out the slide. Okay, so
yes,
this
here.
assumption, so this is the typical bounded gradient dissimilarity assumption actually has the squares, right, in the norms, but actually we can actually show that this bounded gradient dissimilarity assumption with the squares actually imply this one. So so this in other words, the usual assumption with the squares is a stronger one than our heterogeneity assumption.
So you just use it because you can actually show that this is actually a weaker assumption, right?
So I chose this assumption because it can be applied to our analysis. That's the first reason. And then we figure out that this is actually weaker than the usual assumption. Yeah, and that was another plus.
Got it.